Manufacturer ZOYI has kindly sent us unit free of charge for a review. While you are taking a look at the unboxing process of this video, let me tell you my honest opinion about this device. In my opinion, this is the best device that you can buy if you are getting into electronic or as a hobbyist you are working in electronic. This device is a fully functional digital oscilloscope that also comes with a fully functional digital multimeter. So if you are getting into electronics or you are working in electronics in a basic steps, this device is going to provide you all the necessary tools to take a look at the signal or testing a component. While you are having this tool in your possession, most likely you will not need another tool to take a look at the signal, to take a look at the voltage or something like that. Honestly, I wish this tool was available back when I was starting to work on electronics, but right now you have the luxury of buying these tools and be free of buying another oscilloscope while you are starting electronic or buying a digital multimeter. So when you buy this device, you are going to get two birds with one stone, and hopefully by the end of the video you will see that this device is meeting all of its specs. It's correctly spec, which in this nowadays is not something that we take for any device that we buy. Usually Chinese manufacturers would like to exaggerate what they put in their devices. So if the spec says 10 megahertz, most likely your device is going to be 2 megahertz, but you will see that this device is not subject to that problem. In this video, first we are going to take a look at the oscilloscope section of this tool, then we are going to take a look at digital multimeter section of this tool, and at the end we are going to open this tool and take a look at the inside, what is inside this device and what is make this device work. And by the end of this video, I hope this video helped you if you want to buy this tool. Stay tuned for the rest of the video. Now let's imagine this is the first time you are using this oscilloscope, or any oscilloscope for that matter. First time you are using an oscilloscope, you need to calibrate the probe that comes with an oscilloscope. Procedure of calibrating that probe is extremely easy and you don't have to worry about anything. As you have seen in the unboxing section of this video, this tool comes with a variety of things you can use with it. For example, the oscilloscope probe itself, the multimeter probe, a temperature probe, USB charging lead, and of course the manual. Because I don't want any crackling noises on the video, I'm going to pause the video over here and I'm going to take out this oscilloscope probe from its bag. Alright, this is everything that was inside that bag. As you can see, this is just a generic or digital oscilloscope probe. I'm 100% sure that all of you have worked with this kind of probes before. Just in case you haven't worked with this kind of probes, this end connected the oscilloscope and this side is the one that you will use to connect your part of the circuit that you are checking the signal with it. This is the ground lead. You connect it to a ground, and in reference to that ground that you are connected, you will check the signal with the probe. If you don't want to use this hook side of this probe, you can also remove this top side and use it with a sharp point directly pointed to the PCB or wherever you are checking the signal. It also comes with the two tips that you can use for protecting the tip of your oscilloscope probe, and also with color bands which is mostly used for digital oscilloscope with multiple channels. While you are using two or multiple probes at the same time, with these color bands that you see on this oscilloscope probe, you can differentiate the color of the signal on the LCD display. Because this tool has only one channel, we will use one channel, and the channel one is always yellow in most of the digital oscilloscope apps. Right now, the only important factor for us regarding this probe is the bandwidth, and as you can see on the manual, the bandwidth has been stated as 60 megahertz bandwidth. Now we are going to connect our probe to our oscilloscope and then calibrate our probe. As you can see, this oscilloscope has some ports on the sides of it. On the top side, there is the oscilloscope port, the BNC for oscilloscope probe. On the right side is the test signal for calibrating our probe, and also the USB-C connection for us. First, we will connect our probe using the BNC on the top. Connecting is super easy. Then we will turn on our oscilloscope. After our oscilloscope is on, we need to connect our probe to the test point on the right side. As you can see, the symbol of ground is clearly mentioned for us on the cover of this port on the right side. We will connect the alligator clip on the ground side, and we will connect the tip to the other signal point. It is a little bit hard for me to see through the camera. After we connect our signal, as you can see, the edge of our signal is not very square, and this is what it means when we say we need to calibrate our oscilloscope probe so we get a perfect signal with it. We will use the provided screwdriver for this purpose. We will put it inside the hole on the probe and slowly and gently turn the pot inside the oscilloscope probe. When the signal is perfectly squared, we are done with the calibration. If we go further, we will see that our signal will start turning the other way, and it's still not square. At the point that our signal is completely square, we are done with the calibration, and this probe is ready to use with this digital oscilloscope. Now we are going to take a look at some signals using a signal generator. For testing the capabilities of this digital oscilloscope, I have connected it to our signal generator. Let me get closer to the LCDs. We're going to turn both of these devices on. We are going to make some signals with the signal generator, and we are going to take a look at those signals on the LCD of this digital oscilloscope. Right now, what we are seeing on the digital oscilloscope is the residual electromagnetic field on the room, while our probe wire is connected to this digital oscilloscope. Is kind of acting like an antenna, getting all the signals. We are setting the signal generator to output a sine wave at 1 megahertz frequency. I'm going to turn it on. As you can see, there is something on the display, but it's not very visible what it is. There is an auto button on this digital oscilloscope and any other digital oscilloscope that you can buy. While we're clicking on that button, it's going to find the best setting to show the current signal on the display. As you can see, we can see the signal on the display. If we want to get any closer or make it bigger for us, we can use the up and down, left and right button on this digital oscilloscope to make this signal bigger and see more details on the signal. As you can see, we can make the signal bigger and we can open it even more to see more details on the sine wave. I'm going to increase the frequency and see what happens while we are increasing the frequency. 2 megahertz, 3 megahertz, 4 megahertz, 5 megahertz, 6 megahertz, 7 megahertz, 8 megahertz. Right now, while the signal is getting smaller on the display, let me make it a little bit bigger. This is the maximum that we can go. 100 nanosecond is the maximum amount of time base that we can have from this digital oscilloscope. Right now, we are at 8 megahertz. 9 megahertz and 10 megahertz. Right now what you are seeing on the display is a jumpy signal. It kind of resembles the sinusoidal sine wave that we are outputting with this signal generator. But let me tell you that this might not be even the fault of this device, because we are using long wires and I'm using the probe itself as a source of providing the signal. This might be just because of the wiring of our setup. As you can see, if I touch the wires or make it move a little bit, the signal is going to change its shape slightly. So this might be even because of the wires. The important thing is that right now we need to check the bandwidth of this oscilloscope. Whenever we want to check the bandwidth of any oscilloscope, the thing that we are going to do is to give it a sine wave. At a certain frequency, the amplitude of the signal that we are feeding to the oscilloscope is going to drop minus 3 dBi. At that point, we are reached the bandwidth of that oscilloscope. In a more simple sense, right now we are giving this oscilloscope a sine wave. This sine wave peak-to-peak voltage is 10 volt. As you can see over here, the amplitude is 10 volt. And what we are reading over here is around 9 volt. Whenever this voltage drop 3 unit from the voltage that we are giving it, it's gonna be the bandwidth of that oscilloscope. Right now, while we are giving this oscilloscope a 10 volt peak-to-peak signal, the drop on the oscilloscope is around 1 volt. We need to make it around 3 volt to determine the bandwidth of this oscilloscope. This signal generator of mine can only go up to 30 megahertz, and right now I have gave that 30 megahertz to the oscilloscope, and as you can see, the signal hasn't reached that minus 30 dBi that we are looking for. So in a technical term, this device has more bandwidth than that 10 megahertz that they have gave it on the manual. But keep in mind, while a company claims that their device is 10 megahertz, we will most likely use it for 7.5 megahertz signal. And as you can see, a 7.5 megahertz signal on this display is completely visible, and we can see the signal perfectly fine. Now we are going to try to generate some other type of waveform on this oscilloscope. For example, this is a ramp signal with the frequency of 400 kilohertz. As you can see, we can clearly see the signal on this display. Or for example, if we go to a square or a pulse signal, right now, as you can see, we can clearly see the signal on the oscilloscope. There is a little bit of noise on it, but as I said, it might be because of the cables. If we are diagnosing anything, we can see the signal clearly, and it's not going to affect our work at all. Alright, now that we have checked some signals on this digital oscilloscope, let's see how many functions that this oscilloscope has, that when we are taking a look at the signal, it can be useful for us. As you have already seen, this device has a few buttons that with those buttons we can change the time base or voltage. With these buttons we can make our signal smaller or bigger, and it also has the auto button. This auto function can bring the signal to the display while we don't know anything about the signal, or it can be very faster than manually adjusting the signal. Also, this tool has trigger button. While we're clicking on the trigger, this green line on the display is going to be our trigger. If we use our up and down button, we can change the trigger of our signal at that certain level. While some of the signals like this sinusoidal doesn't make any difference while we're changing our trigger. If we, for example, go to a pulse, right now on this signal, if we change our trigger, you will see that the starting point of our signal is going to change with that trigger. And if I make that trigger go above the display, you will see that our signal become bouncy and it jump around, as you are seeing over here. So we can change the trigger of our signal using the trigger option. It also has another types of trigger. If you click on menu, we change the trigger over here. We have the normal trigger, we have the single trigger, which while we are taking a look at the signal and we just want to capture that portion of the signal while it's happening once. And we have the auto function. As you can see, we can see the signal on the display. Also, we can change the trigger type. Trigger can be on the falling edge or the rising edge. We can change the type of our probe. I have already set this to times 10. We can change the language of this device. They have Chinese and English. We can cancel the auto off function so it doesn't let the device turn off. And also, we can change the backlight of the device by some increment. 30%, 50%, 80%, and 100%. And there is an option for more measurements. If you click on this more measurement, there are going to be some more measurements on the display showed for us. Also, we can change the trigger type to DC or AC. And there are also some useful information on the display. Right now it says run, which signal is running. If I turn off the signal, you will see that it disappeared. But if I hold the signal, and you will see that the stop sign, even if I turn off the signal, it's still showing on the display. It will show us sampling section. It will show our time base. It will show our voltage divisions, and it will show us trigger level. As you can see, we can see some useful information on the display and also the battery level that indicates how much battery left on the device. From what I've told, it's gonna be 6-hour runtime on this device on a fully charged battery. Right now, I am done with the oscilloscope section of this tool. Let's go take a look at the digital multimeters of this tool and see how well and how accurate that part is. For testing digital multimeters, a while ago we have come up with this box. This digital multimeter test box has some precision parts on it that we can check. Here is a close-up of this box. As you can see, there are some precision resistors, precision capacitors, diodes, and also some voltages that we can check with our digital multimeters. Something I forgot to mention, the power of this device is extremely fast. As you can see, in less than 3 seconds, device come up. And then we can go to digital multimeter section. And then we can go to multimeter section. Let me brighten up the display a little bit so it is more visible. Alright then, we will begin with the resistors. For this function, I'm going to put it into resistors. Then we are going to check the resistors on this box. You have a common point in the middle. Then we are going to check these resistors. This one is exactly 0 ohm. As you can see, the residual is extremely small. Then we have 2.2 ohm. Takes a while for it to come down, but we are very close. Then we have 22 ohm. Then we have 220 ohm. Then we have 2.2 kilo ohm. Then we have 22 kilo ohm. Then we have 220 kilo ohm. And at the end we have 2.2 mega ohm. By the way, we have a chart from all the digital multimeters that we have checked on our website that shows all the results from every digital multimeters that we have checked. Next, we are going to go to capacitors. Okay, this is buzzers. This is latched and extremely fast. Then we are going to go to capacitors. For capacitors, we have 33 picofarad, 330 picofarad, 3.3 nanofarad, 33 nanofarad, 330 nanofarad, 3.3 microfarad, 33 microfarad, and finally 330 microfarad. Keep in mind the tolerances of these capacitors, and also the larger the capacitor, the more time it needs to adjust to take an accurate measurement. Now we are going to go to diode section. This is a Schottky diode. This is a rectifier diode. This is a red LED and it's turning on. This is an orange LED and it turns on. It is a yellow LED and it's on. It's a green LED and it's on. It's a blue LED and it turns on. This is a white LED and it turns on. Let me quickly test the open circuit voltage of diode test. For this purpose, we will use this multimeter. An open circuit voltage for testing diodes is 3.2 volts. Now we can test some voltages. Testing the voltages, as you can see, the lights on over here is on. We go to voltage. We have 50 millivolt. Sorry, the middle point wasn't making a good connection. We have 50 millivolt. Interesting that it hasn't changed to millivolt. We have 100 millivolt. We have 200 millivolt. I am in the wrong mode. This is the millivolt section. Sorry, it was my mistake. We have 50 millivolt. We have 100 millivolt. We have 200 millivolt, but it appears that the millivolt section is only working up to 100 millivolt. Let's go back to volt. 200 millivolt, 400 millivolt, 1 volt, 2.5 volt, 5 volt, and finally 7.5 volt. And this is the test that we can do with this box. For current test measurements, we are going to use our DC electronic load to test some currents with this digital multimeters and oscilloscope. Something caught my attention while we were checking our test box. As you can see, the maximum, minimum, and the average measurements of the things that you are measuring is always measured on the bottom side of this display. And also this bar graph, it appears to be the same speed as updating the display. It doesn't seem to be any faster than updating the digits on the display. Now we are going to check some current with this device. For checking any current with this device, we have our power supply on the right side providing 5 volt at 5 amp, and we have our DC electronic load to take exactly as much as current as we are asking this device to take. Right now we are set for 50 milliamp. If I turn on this load, you will see that the measured current is almost exactly 50 milliamp. Because this is a very small current and this device is designed to take high amount of currents and it's not very accurate as low amount of currents, we are not going to take this measurement as a fault of this device, but just keeping in mind that our DC electronic load is designed to take high amount of current. Now we are going to go for 100 milliamp. This is 100 milliamp. Now we are going to go for 200 milliamp. Alright, as you can see with the 200 milliampere, we are overloading the milliampere range. There is something I would like to talk about over here. Some people I have seen that they put the multimeter into the milliampere range and they go to the ampere range on the selection, and they will say that the display is showing something wrong, or vice versa. They put the socket into the ampere range and they go to milliampere range and they say the multimeter is not measuring something correctly. When you are doing something like this, like you are in the wrong socket and you are in the wrong section of the software, it is almost that user error. It's not a fault of the device. Right now we are in the ampere socket and in the milliampere range, which is incorrect. Should go to the ampere range. So these two matches, after these two matches, we are going to get a correct measurement. Right now we are going to go for 400 milliampere. And then we are going to go for 500 milliampere. Then we are going to go for 1 ampere. Then we are going to go for 2 ampere. And finally, we are going to go for 4 amp. Alright, so far I have shown you that the digital multimeter section of this tool is also capable of measuring any type of measurement that the digital multimeter can do. Right now we are going to go tear down on this device and see what's inside. Alright, now that you are watching me struggling opening this device, let me tell you that everyone knows that I am a fan of ZOYI technology tools. I have many of their multimeters and clamp meters. This tool was provided to me free of charge, but of course, because I like this device, I like their company, I like their technology. Most likely in future, I'm gonna buy more of their tools, and I am looking forward to some of the new tools that they are made. Because the company kindly offered this tool free of charge to me, I'm gonna leave some of their company links in the description. If you wanna buy these tools, you can directly buy it from them, and they are going to send it to you via the websites that you are seeing in the description. At this point, I would like to take a short break, check all the ICs on this PCB, see how they work, and come back to you with a little bit of explanation, and then we can finish this video. Alright, some time has passed and I have checked the ICs on this PCB. Clearly, this board has been made in 2 separate sections. One side is the digital multimeter section. As you can see, this is the side that belongs to the digital multimeters, and it is clear that the data is coming through this device, and this is the isolated power providing the power to the digital multimeter section. There is also a TP4056 IC over here for charging this battery. I hope this battery has internal protection, because I don't see any internal protection over here. Let me check. Yes, I can see that this battery claims that to be protected, and if I take a wire and connect the 2 terminals of this battery together, this battery has protection and this wire doesn't even get hot. As for the oscilloscope section, all the magic is happening under these 2 cans. Unfortunately, I'm not going to be able to open them. I tried, as you can see over here, but looks like my soldering iron is not even getting hot enough to remove this shield. Also, the marking of this IC has been etched away. I have seen on other YouTubers video that this is a 32-bit microprocessor, and this is the memory related to this processor. So everything seems to be in order. This PCB is well designed. 2 concerns that might have effect in future if we are using high voltage with this device. One of them might be this screw that is extremely short with this 2 terminal, but to be honest, it's not a problem for me because I'm never going to be using my device with high voltage, and my area of work has been lower voltage than, I don't know, maybe 100 volts, so this is not a problem for me. But if you're using this device with high voltages, like, I don't know, 600 700 voltage, you might be taking care of this screw. Just simply remove it or put a plastic screw in its place. It's going to be perfectly fine. Other than that, I don't see anything. The digital multimeter IC is this one. It has a marking on it, DM1109EN. I guess. About the usefulness of this device and the quality it's made, honestly, I wish something like this was available back when I started to work on electronic. This device is a very good device especially for anyone who wants to join electronic, anyone who wants to start electronic. It's going to get rid of any needs for any digital multimeters or any oscilloscope, especially for beginners or hobbyists. At this price point, I am very satisfied with the quality of this device and usefulness of this device. But of course, this is just my opinion. You can have your own opinion. You are entitled to have your own opinion. If you like something, you like it. If you don't like it, well, it's totally up to you. This is my honest opinion about this device, and I'm pretty sure I'm gonna use this device on my projects in future. Thank you for watching this video. I hope this video has been useful to you. I hope this information that I provided to you is gonna help you make a decision easier. See you in another video. Well, thankfully I haven't killed it yet. Over here I have created a practical example to show you how useful this device can be. As you might know, one of the most beneficial parts of electronic engineering is designing and making switch mode power supplies. Of course, after we designed our switch mode power supply and we made the first prototype, we would like to take a look at some signals on that PCB. Of course, we can do that with the oscilloscope section of this tool. Also, we would like to check the output voltage of our switch mode power supply. We can switch to the digital multimeter section and check the voltages. And if you want to check the current on this switch mode power supply that we designed, we can switch to the current section. Right now I am using a resistor as just the dummy load. We can of course take a look at some currents too. And most importantly, if you want to take a look at the changes on the switching signal while we are putting the device under load, of course we can do that. We can go to the oscilloscope section, put some load on our power supply.